All right, now time for the most important part of learning how to do simulations. This is the portion where we need to create our mesh. So, in a finite element simulation, the before you do any solving, you need to specify where these elements are that you're going to find the solution on. So, if you're doing a linear analysis, it'll basically like find this. It's only really calculating the temperature at the edge or the vertices of the elements, and then it's interpolating everything else that's in between. In a second order approach, so actually in this simulation I have a second order solution that I'm asking for. In this one, it's actually going to try and create a parabolic interpolation. So for a parabolic interpolation, it's actually got some nodes that are on the edges of the element in addition to like on the vertices. So we need to specify like what those elements are. So the most important advice I can give you for this is that you want elements that are small in regions where you expect rapid variation in whatever you're solving for. So in this case, that's temperature. So in the regions where you expect like a rapid change in temperature, you want to have lots of elements in that region so that you can resolve that change and interpolate it correctly. So for example, like I know in this case that the radius of my Gaussian spot is approximately half a meter. So what I wouldn't want to do is create elements that are 1 meter in size. I wouldn't be able to see the Gaussian at all in that region. My general rule of thumb is that I like to have at least like 5 elements spanning a region where I expect rapid variation. And preferably a lot more than that. So, for example, like in this simulation, I have highlighted. So the reason why I put this face on here is so that I could visualize it. So this face has a diameter of 1 meter, and since my Gaussian beam has an approximate like characteristic radius of half a meter, that means its diameter is about 1 meter. So my Gaussian laser is going to rise and decay over the course of approximately this spot. Now it's going to be a little bit wider than that because a Gaussian technically goes to infinity, but most of the action is going to be happening where this, like in the region where this circle is. So I'd like to have lots of elements in that region. I guess like if I'm looking at this, like if I want to make a smooth plot, I might like to have, I don't know, something like 20 elements across there. So just like think about that, like when you are creating your mesh. On the flip side of that, I expect that if I go far away from that Gaussian, there's probably not much going on, like very far away. So like if I go, let's say 5, so I think I said that this is a 5 meter radius hemisphere. Like a Gaussian that has a radius of half a meter, if I go 5 meters away, like that means that like the size of the heating is going to be, I don't know, like something like 5 orders of magnitude smaller out there. So I don't expect that the temperature in this region is varying very quickly. So I might be okay with having a 1 meter sized element way out here. So like the objective of a finite element simulation is to design a mesh that has a lot of elements in the regions that you care about and like where things are varying rapidly, and many less elements in these other regions. So like that's the ideal mesh.